Yeah, I don't know if I've had enough coffee yet to answer any tough questions. Must say anyway, I'm quite humbled to be invited to speak here. You know, it's sort of weird giving a talk on architecture at a conference put on by SEI, you know, given their massive contribution to the whole theory of architecture. So it's a pretty humbling experience, and I'm excited to be here. So this talk is, you know, it's an attempt to define the microservice architecture. You know, that term gets thrown around a lot, and you know, every so often I have conversations with people, and it's clear that there's not necessarily a universal understanding of what a microservice architecture is. You know, it leads to questions like, can I use a microservice for this? And it was after spending a whole bunch of time with a client hearing those questions, and it was like, there is no such thing as a microservice. You know, and I'm going to attempt to justify that claim. Anyway, so that's my talk. A little bit about me. So I actually live in the San Francisco Bay Area, in Oakland to be precise. And I got my start in programming back in the mid to late 80s building Lisp systems. You know, everything from compilers, runtimes, garbage collectors, and all of that. Lisp being that language with lots of parentheses and so on. And did that for a number of years. And then actually, you know, it's funny, I switched over to C++, which was kind of a questionable decision, but got paid more. But eventually, you know, I ended up programming in Java. And then 10 years ago, my book Pojos in Action came out, and that was all about building enterprise Java applications with Spring and Hibernate, which, you know, 10 plus years ago were revolutionizing how we build enterprise Java applications. And then shortly thereafter, I started playing around with this obscure service known as Amazon EC2. You know, an evangelist from Amazon came to talk about their APIs at our local Java users group. And we thought they were going to talk about APIs for buying books, and instead it was APIs for provisioning servers. And the notion that 10 years ago, with one API call, you could provision 20 servers and pay 10 cents an hour just sort of blew my mind, right? And so much so that I ended up creating a startup called Cloud Foundry. There was a Java platform as a service, so with like 11 clicks of the mouse, you could deploy your WAR file on a cluster of EC2 servers with Apache Tomcat and MySQL set up. And then that was acquired by SpringSource back in 2009, shortly before SpringSource was acquired by VMware. So I was at SpringSource, VMware, and then Pivotal, where various assets were spun out for a number of years. And then about 3.5 years ago, I left, and these days I just focus on the microservice architecture. And that was something I had got interested in because there was a lot of synergy between PaaSes like Cloud Foundry and the microservice architecture. So I do consulting and do training, and I also have a startup called Eventuate, and we're building a platform to simplify the development of transactional business applications that use the microservice architecture. And I'm also writing a book, Microservice Patterns, after swearing that I would never write a book again because it was such a traumatic experience. So the trauma is you know, sort of declined somewhat, and I'm embarking on this project. And the first few chapters are available in MEAP, Manning Early Access Program, so go check it out. And if you want to know more about microservices, go check out learnmicroservices.io, and that links to a whole bunch of resources, code, articles, videos. Also, you get from there to microservices.io, which is where you'll find the pattern language. Anyway, so that's sort of me. So the agenda is brief refresher on software architecture, kind of sort of to define some terms, which, you know, it's sort of at some level it's kind of architecture 101, though I think today many of us, we kind of forget about what words like architecture mean. So it's just kind of useful to revisit that. Talk about the monolithic architecture, microservice architecture, define those in terms of sort of architectural kind of concepts, talk briefly about why the microservice architecture is not a silver bullet. And then I'm going to finish up by talking about one of the distinct challenges in a microservice architecture, namely how to manage your data, how to ensure data consistency across multiple services, and how to do querying. Because as you're going to see in a microservice architecture, those two sort of basic things become somewhat of a problem. And coincidentally, I'm going to actually talk about event sourcing and CQRS super briefly, and I'm excited to see that later on this afternoon there's a much more in-depth talk on that. Okay, so let's get going. So, basic definition, it's like, what is software architecture, right? And, this is sort of the classic definition, and, I suppose the critical key part of this is a set of structures that you need to reason about a system. So it's some elements and relations or relationships between them, and then the elements in the relations, they have properties. So you could kind of summarize that as architecture is this sort of triple of elements, relations, and properties. Or you could just call it a set of boxes and lines, right? I see a lot of that. People draw boxes and lines, and that's your architecture. Obviously, those boxes and lines have to have specific meanings. And then for that reason, you can sort of view the architecture of a system as sort of being multidimensional. So in the same way you think about the structure of this building, if you're sort of the architecture, there's many different aspects to that. There's the concrete and steel, the structural aspects of the building. But if you're an electrician, you're interested in the electrical architecture. Likewise, if you're a plumber, you're interested in where all the pipes and stuff go, right? And then there's sort of some mechanical aspects. Just guessing here, I have no real idea on how buildings are constructed. But you can at least imagine that there are like a set of blueprints, and different people will use different blueprints based on what they do, whether it's structural, electrical, plumbing, etc. So you can sort of that kind of leads you to the view model, right? So to describe the architecture of a building or the architecture of a software system, you actually need multiple views for different perspectives. And then, of course, each view is itself a set of particular kinds of elements, relations, or relationships and properties. And then, of course, the most sort of classic way of describing architecture is the 4+1 view model. It's kind of created back in the ancient history of software development. And here you've got 4 different views. That's the 4+1, which are the scenarios which animate the views. So pretty it's actually fascinating. I haven't actually encountered a reference to this in sort of everyday literature in quite a long time. So it's kind of interesting to go revisit this topic. So you have the logical view. So that's primarily concerned with functionality. So it's we're building systems using object-oriented languages. So the logical view is your classes, the packages, and the relations are relationships between classes or between packages. Associations, inheritance, dependency, and so on. So that's the logical view. Then you, of course, have the implementation view. So that code that we as developers write, the classes and the packages, are somehow turned into modules and components by the build system. So in Java, you would have modules like jar files, perhaps built by Gradle or Maven. And then the components are your executables, which in Java could be an executable jar file, or it would be a deployable unit like a war file or an IR file. Or if you're programming in C or C++ or Golang, your executable would obviously be an operating system executable. So that's the implementation view. What are the sort of executable or deployable components of your application? And this actually, you're going to see, ties directly into the monolithic versus microservice architecture. And then, of course, you've got the process view, which is the view of the running system. So each of those deployables or executables are then turned into running processes. And then the relationships between those processes would be some form of inter-process communication. So that's your process view. And then finally, you have the deployment view. Interestingly, it used to be called the physical view, but perhaps because everything's gone virtual these days, a name change was necessary. And the deployment view shows the running machines, whether they're virtual machines or physical machines. And on each of those machines are the processes from the process view. So there's sort of this direct linkage from the logical view to the implementation view to the process view to the deployment view. So those four views define the architecture of your system. And then finally, you have the +1, which are the scenarios. And a given scenario, which is sort of derived from use cases or stories, illustrates how the components or the elements of a particular view collaborate in order to handle a request. So that could be classes or objects, or it could be the executables, or it could be the processes, or it could be the nodes in the deployment view. So you pick a few scenarios. You've got your architecturally significant scenarios that illustrate how this architecture works. And collectively with the views, that sort of forms a description of your architecture. And you'd maybe write an architecture document. So that's sort of the basics of architecture. And then there's this concept of an architectural style, which also you're going to see the microservice architecture, the monolithic architecture is an example of an architectural style. So that's sort of the vocabulary of the components and connectors, sort of from a different book. It's like instead of components, think elements, and instead of connectors, think relations. That sort of can be used in instances of that style. So once again, there's analogy with sort of the physical world where there's particular architectural styles that buildings conform to, right? And so we have architectural styles for software, of course. And then, a classic architectural view is layers. So you've got a set of components, set of elements. Doesn't matter what particular view that they're in. And the layers architectural style organizes those components into layers where each layer has a well-defined set of responsibilities and then also constrains the dependencies. So a layer can only depend upon the layers below it or possibly only the layer immediately below it. So we've got this concept of an architectural style. And then, then the other question is sort of, why do we care? What's the point of this architecture thing anyway? So if you look at the requirements for an application, they obviously fall into two categories: the functional requirements, what the application does, and then you've got the non-functional requirements. So the functional requirements require sort of domain knowledge, deep understanding of the business domain, so you can actually build a system that does the right thing. The non-functional requirements, or the quality attributes, or the ilities, is where architecture comes into play. You can build practically any system. You can satisfy a set of requirements using almost any architecture. Some architectures make it easier or harder, but I think as many as you can actually build implement a set of use cases using a big ball of mud architecture, and it works, right? It's just that you don't actually enjoy developing the system, and you can't develop it particularly quickly, and so on. So architecture really just has nothing to do with functionality, and it has everything to do with these non-functional requirements or ilities. And if we look at a list of ilities, there's actually, if you go to Wikipedia, there's this massive long list of software of different ilities. And I've listed some of the key ones here. And the ones that I'm sort of particularly interested in are the first four. Because those directly affect the velocity of development. So maintainability, evolvability, testability, and deployability, they directly determine how fast you can build and release your system. And then obviously the next three, scalability is pretty important as well. Security obviously is essential. Reliability is also essential. But today, there's this tremendous pressure on businesses to innovate faster. which from an IT perspective means that we have to build better software faster. So those ilities which impact development velocity become absolutely essential. And so that's sort of why, this whole architecture thing, why we're talking about the microservice architecture, because as you're going to see, it is the way in which you build better software faster. It's the primary goal of the microservice architecture is to do that. And even though it was developed at companies who are operating at very high scale, scalability is very much a secondary goal of the microservice architecture. It's all about minimizing lead time, reducing the amount of time between someone having a concept or a requirement and putting that and getting that requirement into production. It's all about increasing the frequency of deployments. It's no longer good enough to release every 6 months or every month or every week. Or, the state of the art today is pushing changes into production many times a day. In the ideal state of development, a developer does a git push, and then 15 minutes later, that change is deployed into production. And there are companies who are doing that. And the microservice architecture is a key enabler of that. So, so if you think about modern software development, it's really a combination of 3 things: process, organization, and architecture. So the process today is, the focus is on continuous delivery or continuous deployment. And that's where the software is, or continuous delivery is where the software is always in a releasable state. And there's a whole set of development practices that you have to follow in order to ensure that. And then there's the variation of that for SaaS companies, which pretty much a lot of software is today. That's continuous deployment. And that's where, as I mentioned, you're continually deploying into production many times a day. You also have to think about organization. That's where instead of having large, sort of slow-moving teams, you have small, autonomous, agile teams, the so-called 2-pizza team, where you've got perhaps 6, 8 people on a team, enough who can sit around a table and quickly make decisions. But they're also autonomous, so all of the skills required to do development, testing, and deployment are all within that particular team. And then the final question mark is, what's the right architecture in order to support this? And to answer that, I want to now look at the whole monolithic versus microservice architecture. So if you think about, the monolithic architecture, from a logical perspective, you're going to build, a system that is nicely layered and modular, right? So this example is a storefront. So you've got the storefront UI, the presentation layer that's perhaps implementing a web application, generating HTML, or it's exposing a REST API. The back end is comprised of a set of modules, each one of which implements a particular business function. So we've got catalog, recommendations, reviews, and orders, etc. So from a logical view perspective, we've got a nice layered and modular architecture. But when we use the monolithic approach to architecture, we package everything up in a single deployable or executable unit. So that could be an executable jar, a WAR file, an IR file, or an operating system executable. So logically modular, but sort of from an implementation view, it's actually a single component. And so that sort of is kind of an interesting thing where, the 4+1 view model comes in. So you can think of the monolithic architecture as an architectural style that structures the application as a single component. So you've sort of got 2 different perspectives here. And what's interesting is that this is not an anti-pattern. If you're building a small application, the monolithic architecture can actually work well. All the various different aspects of development, testing, deployment, and scaling are actually quite simple and straightforward. when your application is small. So in other words, these sort of software quality attributes are good. The problem that you run into is that successful applications have a habit of growing, right? You can start off with a small team and a small application, but over time, your application will just get bigger and bigger. You think about classic software engineering books, they sort of have this thing called maintenance, right? Which sort of implies that you stop development and then you're just maintaining it, which involves like making little tweaks. The reality is that development just continues. Well, either your company dies or the product gets killed off, or you just continue developing it, which means that every day your team of developers are adding more and more lines of code to your product, and it's just getting larger and larger and larger. Seeing how many little animations I got on here. And of course, your development team will get bigger and bigger, because if you're successful, you have more money and you can hire developers. So the rate at which your application is getting larger and larger is just getting, is growing as well. And it's not uncommon for an application to live for many, many years. And it's quite likely that you're going to end up with millions of lines of code. And so this beautiful small application that was just very easy to develop is just turning into this huge system. One company I talked to, they'd been around for maybe 10 years, and they'd actually had this demo, which was so successful that they started shipping it. And then they were a successful company, and say 10 years later, they had 1.5 million lines of code, half of which was actually SQL Server stored procedures, right? And that's kind of a consequence of success. Oh, and you might try and split up your team into sort of smaller teams that are focused on a particular functional area. But just things are just getting bigger and bigger. And I think there's a certain inevitability that sooner or later you will end up in this place called monolithic, what I call monolithic hell, where your system has become so large that it's sort of beyond the capabilities of a developer to understand. And it's likely that the internal modularity of the system has just sort of degraded. It's because people do not understand how it works, it starts to degrade into a big ball of mud. And so you end up in this place where sort of any notion of agility becomes impossible at this point, right? You're just sort of in a world of pain. The business wants you to develop faster and faster, but you just can't. You've sort of outgrown your architecture, and it's painful. And then not only that, you've got this application that's been around for some number of years. You're now in a situation where your technology stack has become obsolete, and you'd like to upgrade, except that you've got this massive code base, and it's simply not practical to try and rewrite it to use a different technology stack. So you've got this massive big ball of mud that's written using technology that's obsolete and no one wants to use. And so, everything about your application, sort of in terms of these illities, is now bad, right? It's difficult to maintain, it's difficult to evolve, it's difficult to test, and it's somewhat difficult to deploy as well. So, and I think there's a certain inevitability about that, and it just comes from being successful. And sticking with the same architecture. And I sort of see this pattern at other levels as well, where, not only do you have a massive monolithic application, you sometimes see code where methods and classes have just kept on growing and growing and growing, because every day a developer has added a few more lines of code, and that method or that class has just got a little bit bigger, and they haven't taken a step back and refactored it into a set of smaller classes or a set of smaller methods. And it's just sort of incrementally grown into something unmanageable. that's the monolithic architecture. It's not an anti-pattern, but it's quite likely that a long-lived application will actually outgrow it. And then that becomes the motivation for the microservice architecture. And that's a sort of different approach. Lots of words on this slide. But the critical part is that it's another architectural style. But instead of structuring the system as a single executable or a single component, it structures the application as a set of services, which is another way of saying executables or deployable components. And then those services are loosely coupled, which, sort of standard modularity argument. Each one can be developed and deployed and tested independently of the other ones. And then the other critical part is that these services are organized around business capabilities. So a service performs a business function. So you can actually show a service to a business person, and they would appreciate the value of that service. So they're not organized around technical capabilities. So this is sort of another kind of implementation view architectural style. And in fact, you actually can sort of view the system as having two different levels of architecture. So at the system level, where you've said, we're going to have these services, they're going to communicate through these APIs using these particular communication mechanisms, that's sort of your implementation view of this architecture. But then each service has its own particular architecture. It's like, it will likely be layered and modular and so on, but it could also use a completely different technology stack. You're no longer constrained to use the same technology stack for all of your services. That's not to say that you should sort of have anarchy and just use arbitrary languages and frameworks and so on, but you actually have a lot more choice. And that's a good thing because it lets you evolve your technology stack over time. It's important to make a distinction between service and service instances. So a service, that is an executable component or deployable component, and then a service instance is that service at runtime. So it's a process. And normally each service will actually have multiple service instances, ideally scattered around on multiple machines not for availability. And you have multiple service instances to also handle the load and so on. And there's some kind of load balancing component. And then, as I mentioned, the services are organized around business capabilities, which is one of those somewhat nebulous terms. But it's a thing that a business does to deliver value. So, a business is actually a term from business architecture modeling. So you can view a business as having a set of capabilities. So an online store would have capabilities like taking orders, managing inventory, managing deliveries, and so on. Quite often the business capabilities sort of correspond to some set of operations around a particular business object. So it's sort of like noun management, but not always. So, so in theory, you get your business architects to create a business architecture consisting of a set of business capabilities, and then you can map those capabilities into services. I don't think there's necessarily always a direct mapping like that. But the idea is that a service performs some particular business function. So in the online store, you'd have order service, inventory management, delivery management, and so on. And what's interesting to note is that I haven't really said anything about the size of the service. It turns out that the term microservice architecture really is a terrible term. Because you should just ignore the sort of prefix of micro, because at some level, sort of this size is very much secondary. You really want a set of services that are organized around kind of business capabilities. And the only bearing that size has is that the service should be capable of being developed by a small team. Small teams are agile, they're fast moving, and that's sort of your goal here. And so your service should be small enough such that it can be developed by a small team. And that's quite different from sort of other definitions. A few years ago, you'd hear people say a microservice should only have 100 lines of code, or it should only be 2 weeks' worth of work. But I think a much more meaningful definition is the one here, where it should be capable of being developed by a small team. The lead time for that particular service, the time from concept to deployed or released code, should be very small, and the frequency of deployment should be very high. And those should be your criteria in determining your services, and as opposed to some arbitrary sort of size-based metrics. So it's sort of like, I would like to call the microservice architecture the service-oriented architecture, except that term has just terrible connotations, right? Sort of SOAP and WSDL and ESBs and all of those expensive vendor products and so on. I think the reason the term microservice architecture arose was primarily because it's sort of a marketing thing. We needed a different term, right? Interestingly, some organizations do have relatively fine-grained services. So Uber have roughly 1,900 services in their system, which is roughly the same number of developers that they have, right? Netflix have like 600 or 700 different services. I think they're much more fine, slightly more coarser grained. And then Amazon, they coined the term two-pizza team, except that, of course, appetites pizzas vary wildly, so it's not a very precise metric. So I think at one point the team sizes were like 6, 7, 8, but they might have actually shrunk down to 2 or 3. So they are finding that you can have some sort of finer-grained services, but it's all, once again, it's all about small teams, agility, minimal lead time, higher deployment frequency, and so on. That's the goal. So let's get back to this thing about no such thing as a microservice. So to me, the term microservices is a sort of linguistic shorthand for the microservice architecture. Certainly when you're speaking and writing, saying the microservice architecture can sound a bit clumsy, and it's nice to abbreviate it to microservices. But as I described, that is an architectural style that applies to an application architecture. And as such, there isn't really this, the term microservice in itself is not a particularly sort of meaningful or useful word. So, when someone says, can I use a microservice for this? That just really doesn't sound, it's sort of not a right use of the word. Or equating a microservice with a Docker container, that's another popular thing, right? I'm using Docker, therefore I'm using microservices. So it's all, you have to kind of just think of microservices as a shorthand for the microservice architecture. And that kind of improves a lot of improves the quality of the discussion around this microservice architecture thing. Because otherwise, if you start thinking of a microservice in a singular sense, you end up having some very strange and unproductive discussions. Except unless you use it as an abbreviation for a service within a microservice architecture. But it's just sort of, it's like the dark side. You want to stay away from that. Finally, here's a slide with a picture on it. Here's the online store reimagined as a set of services. So before there were various modules implementing particular business functions, and now we've got each one of those has turned into a service. So you've got catalog service, review service, and so on. each one of these services, that is a deployable, executable unit. So at runtime, in the process view, there will be many boxes, many processes that are instances of this catalog service. It's important to make that distinction. Each service has its own database. This is another critical aspect of the microservice architecture. In order for services to be loosely coupled, they have to have their own private data, because if two services share the same database tables, they are communicating through the database and they are tightly coupled. They are no longer loosely coupled. And as you're going to see, or as you can imagine, this has huge consequences on how you do transactions and how you do queries, especially because you can't use two-phase commit and you can't use distributed queries. All the data access has to be through APIs at this point. But this is how you ensure that these services are loosely coupled. And then sitting in front of those services are, you'd have an API gateway that acts as a facade. It's the single entry point into the system that basically encapsulates the APIs. It will take care of functionality like request routing, API aggregation. It can expose custom APIs to particular types of clients. So your mobile client will access the service through one set of APIs that get translated into backend calls. Your public API would perhaps be different from the API that the mobile device is used, and so on. What's interesting is you look at a monolithic architecture, it's a set of instances running behind a load balancer. And once you embrace the microservice architecture, sort of the thing becomes a lot more complex. But the good thing is that if you're building a complex system, you end up with a microservice architecture. These quality attributes tend to be extremely good. You actually have a system that is highly maintainable, highly testable, highly deployable, and it could very well be scalable as well. Remember, the primary goal of the microservice architecture is to tackle complexity and not to build a scalable system. Amazon embraced what is now called the microservice architecture, not because they were operating at incredibly high scale, but because they were sort of in this hyper-competitive environment, and they needed to develop better software faster. And so they picked this service, they actually called it, I think, a service-oriented architecture, just so that they could get stuff done quicker. There tends to be some scaling benefits as well, but they really are secondary. So sort of to complete the picture, right, you've got continuous delivery deployment as the process. The organization is small, agile teams, and then your architecture is the microservice architecture. The microservice architecture directly supports continuous delivery because your services are testable and they are deployable, which is sort of two essential requirements for continuous delivery. And also the microservice architecture directly supports the notion of having small autonomous teams. Each team is responsible for their service that they can develop, test, deploy, and operate independently of all of the other services. They're no longer having to contribute to the same sort of overall code base with all the other teams that really destroys any notion of autonomy. So these three things really go together and enable you to build better software faster. And then lastly, this actually enables you to evolve your technology stack. When you're implementing a new service, you can pick a new technology stack. When you're making major changes to an existing service, you can rewrite it to try a new technology. Not only that, if it doesn't work out, if you start using Golang because you heard that Google uses it and it's really cool, and then you decide that sort of, C, a 1990s version of C, is too low level for what you want to do, and you wish you were using Scala, it's not a disaster. You've just got one service that's implemented using this language that you basically have decided, instantly decided you're going to deprecate in your system now. And that's hugely valuable. It's not a disaster. Okay, so the microservice architecture has a bunch of benefits, but it's not a silver bullet, right? Fred Brooks coined this term 30 plus years ago. There's no perfect technology that sort of that will solve all of your problems. And with the microservice architecture, there are a lot of challenges. And by far, the biggest challenge that you have is complexity. You're now building a distributed system. So you have to deal with inter-process communication, whether that's REST, gRPC, messaging. You have to deal with partial failure. The service you invoke might not be available. Not only that, your database has been sliced up and distributed amongst a bunch of services, and you can't use distributed transactions or distributed queries. That's complicated in a way. Testing can be challenging. Potentially many more moving parts that have to be deployed in a test environment. Deployment is a challenge. So rather than running n copies of a monolithic application in production, you've got tens or hundreds of services and multiple instances of those. And so there's a lot of moving parts that need to be managed and monitored, etc. The good news is for all of these, there are frameworks and techniques and that can actually address many of the issues, but it's still a challenge. So it really is important to ask the question, is the microservice architecture a good fit for my application? Because adopting it is not something that should be undertaken lightly. There's a lot of consequences and complexity that you now have to deal with. So it's like, sort of number one, it's like, how do I break up my system? And then how do I deploy it? And how do I deal with how to inter-process communication? And so on. So there's actually a whole bunch of different issues that you have to address. And not only that, there are different solutions to each of these issues with their own set of trade-offs. And so the answer is to all of this. It depends, right? It really does. So to help with this, I've actually been working on a pattern language for the microservice architecture. So a pattern, of course, is a reusable solution to a problem. So you can apply it over and over again, which is good, and it occurs in a particular context. So you always have to take into account the context before picking the solution. And the structure of a pattern is incredibly valuable. It provides real guidance. Obviously, a pattern has a name. It describes the situation within which you're trying to solve the problem. Different situations actually might require a different solution. It describes the problem. It describes the forces. These are the issues that you're trying to address. And they can be conflicting, so you actually have to make trade-offs. Obviously, the pattern describes the solution. So rather than just sort of saying, use the microservice architecture, sort of by structuring it in the form of a pattern, you're providing a lot more information that can help guide you in deciding whether to use it. And then not only that, the pattern also has to describe the resulting context. What are the consequences of applying this pattern? And as you're going to see, that's hugely valuable. And then it also has to describe what patterns are related to this pattern. So if we look at the resulting context, you have to describe the benefits. That's what people tend to focus on, right? But it also requires you to describe the drawbacks. What are the downsides of applying this pattern? So in the case of the microservice architecture, it's complex, right? And then you have to describe the issues that you need to resolve after choosing this pattern. So, if we look at the microservice architecture, right, I've sort of described the benefits. I've mentioned that the major drawbacks are complexity. And now you have a whole bunch of issues around well, decomposition is one, and implementing or developing, testing, and deploying a distributed system. So there's like this massive long list of issues that you have to address. But by sort of explicitly sort of documenting those issues, it actually enables the reader to sort of objectively decide, do I want to go down this route, right? And we a lot of discussion around technology tends to ignore the drawbacks and the issues, right? It always focuses exclusively on the benefits, which sort of leads to things like, well, sort of the Gartner hype curve and sort of technology's not working out too well, at least initially. And then the other critical part of a pattern is the related patterns. So there's two types of related patterns. There are patterns that are alternative solutions to this particular problem. So the monolithic architecture is an alternative to the microservice architecture. And then there are the patterns that solve the problems that are introduced by this pattern. So, applying a pattern creates issues. These related patterns then are the ways of solving these issues. So by including that in the description of a pattern, you're enabling the reader to then solve the problems that they've just created for themselves. So you've got these sort of successor patterns. So, so basically you end up with a web of patterns, and in the case of the microservice pattern language, this is it. I can't even read this. So if you go to microservices.io, you can see a much more readable version. Well, basically, there's sort of various groups of patterns. So there are these, what I'm calling the core patterns, which are the monolith versus microservice architecture patterns. So that's your high-level choice. Which architecture do I want for the system? And then if you do pick the microservice architecture, then everything else are patterns that solve the problems that you have just created for yourself. So there are patterns around deployment. You've got tens or hundreds of services to deploy, and so sort of handcrafted, manually configured servers isn't going to work anymore. There's a whole set of patterns around communication style, REST versus messaging, for example. Patterns around service discovery. How does one service find the IP address of another service? No longer a trivial problem that can be solved by a configuration file with hard-coded IP addresses. Patterns to do with how to communicate with the outside world. That's the API gateway pattern. Patterns around observability. Your system is much more complex. How the heck do you tell what's going on, right? Basic techniques like log aggregation, distributed tracing, and so on are actually the solution there. And there are some patterns around testing. And that's an absolutely fascinating issue because, in theory, in order to test a service, you have to provision all of its transitive dependencies. But that would be sort of slow and brittle. And so there are patterns for testing in isolation. So you can just basically do a unit test of a service. And then there's a whole set of patterns around dealing with distributed data. This sort of lurking problem that you've now created for yourself. And actually, there's two of those patterns are in fact event sourcing and CQRS, which I want to talk briefly about because it's an absolutely fascinating topic. And I'd encourage everyone to go to this afternoon's session to find out more. And hopefully we're going to be in an agreement about that. So that's the pattern language. Go to microservices.io to find out more about that. And in the remaining time, I just want to talk briefly about how to deal with distributed data. So, rather than having a single database that all of the services access, and in particular having tables that are shared amongst multiple services, in order for the services to be loosely coupled, each service basically needs to have its own private data, its own private tables, in other words, if you're using a relational database. So the order service has, its tables. The customer service has its tables. They can still perhaps share a database service, so it doesn't mean having to go get 10x more Oracle licenses or anything like that. But it's like the data has to be private, and all communication has to be through APIs. And that sounds great, except that in a system, you typically will have the requirement to maintain data consistency across multiple services. So here's an example of an invariant, right? Like, customer has a credit limit, which means that if you sum up the totals of all of the open orders, it cannot exceed the credit limit. So in order to, when you're about to create a new order, you have to make sure that this new order will not exceed the credit limit, right? And this is exactly what we use ACID transactions for. They're a wonderful thing, right? So if we were using a sort of traditional sort of monolithic database, you'd just do something like this, right? Begin a transaction, find the existing orders, find the customer's credit limit, do the calculation to see whether you're going to exceed the credit limit and create a new order. And then you commit the transaction. And even if there are multiple simultaneous attempts to create orders for the same customer, assuming you have the right isolation level and your database will serialize those transactions and ensure that this business rule is enforced at all times, right? And it's sort of like this trivial problem in the context of relational databases and ACID transactions and all of that. But you can't do this in a microservice architecture. Orders and customers are in different databases. So that's number one. And then in order for this to work, you'd actually need some form of distributed transaction. So that's a problem. And it turns out for a whole bunch of reasons, two-phase commit XA distributed transactions is not an option for modern applications. Systems that we build today just don't use it. You got the CAP theorem that basically says you have to choose between consistency and availability. People prefer their systems to be available. Many modern database and sort of infrastructure technologies like NoSQL databases, modern message brokers don't support distributed transactions either. So even if you wanted to, it's a problem. So the solution is to actually use what are known as sagas. Sagas concept there was a paper on sagas, I don't know, was it in the 80s, something like that? And there they were talking about long-running transactions and how they would hold locks for a long time, which would be bad, and so you should chop long-running transactions up into a sequence of local transactions, and that will sort of increase the liveness of your system. So here we're actually using distributed sagas. So instead of a distributed transaction that spans multiple services, instead you have a saga which consists of a series of local transactions in multiple services. So something happens in one service, it publishes an event or a message that triggers a local transaction in another service, which then it emits a message which triggers a local transaction in another service. So it's a very different transaction model. And with this sort of credit checking case, it would work like this, right? You've got the order service, request comes in to create an order. It would actually create an order in this sort of pending state, emit an event to say that the order has been created. That triggers a local transaction in the customer service, which then reserves credit. We've actually even put some credit reservation tracking functionality in the customer service. And then that service will emit an event indicating the outcome of this credit reservation. Either the credit was reserved or the credit check failed. So we've got two local transactions, one in each service. The second one triggered by a message or an event produced by the first one. And then that will trigger, that message from the customer service will trigger a transaction that will then either approve or reject the order. So instead of one distributed transaction, we've got these services exchanging messages that trigger a transaction. So that's sort of the basic approach that you need to use here. There's an interesting little problem with this, is that in order for that to work reliably, a transaction has to atomically update the database and publish a message. And that is something that you would normally do with two-phase commit. Begin a transaction, invoke your JMS message broker, and then update your JDBC database and commit the transaction. So there's sort of this sub-problem of how to atomically update a database and publish a message. And so there's this approach called event sourcing that does this. I'm skipping over a whole bunch of steps, but go to the talk this afternoon. And that's an approach where you persist your domain objects by storing events. So like an order would be persisted as an order created event, followed by an order approved event, followed by an order shipped event. This is how you would store the state of the order. And then whenever you needed to reconstruct the current state, you would load those events for that order into memory and replay them, basically do a functional fold over that stream of events to reconstruct the current state. Think of summing up all of the credits and debits for a bank account. And this is an approach, this approach has many benefits, things like auditability and so on, but it also solves this problem of how to atomically update state and publish events, because all you're doing is saving events into this event store. So it kind of supports this saga mechanism very naturally. The other problem, which I'm going to talk about briefly, and then I'm done, is how to do queries. So imagine that you want to find recent high-value customers. In a monolithic system, that would be trivial using a query like this, join between customers and orders with the appropriate where clause. But in a microservice architecture, customers and orders are in different databases. And then it turns out that if you've used event sourcing, there isn't a column which says order state. The only way you can get the state of the current state is by folding those events together. So your where clauses would look very, very weird. You'd have to have a nested select. So trivial queries like this are no longer easy. And that then leads to this second pattern, CQRS, command query responsibility segregation. So you have commands, the post, puts, and deletes, and you have queries, the gets. And so you actually structure the system so that the queries are done against a materialized view. So given that our collection of events is unqueryable, or the data that we want to query is scattered across multiple services, we maintain one or more views by subscribing to the events that are coming out that are produced by the sort of the system of record, which might be using event sourcing. So we build up one or more of these materialized views. So you end up with a system architecture that looks like this. You've got your command side that's handling the creates and the updates and deletes. And then you have a whole set of different views that are handling particular kinds of queries. This is, in fact, like a generalization of a technique where you'll use, say, MySQL as your system of record, and Elasticsearch or Lucene or Solr text search engine to do your text searches, and you have to synchronize the two. So that's the architecture. And so events flow out of the system of record and then update these various views. So this is a way of basically doing queries that join data across multiple services in a microservice architecture. So, and it has benefits. So it means each one of these views is optimized to a particular type of query. So you have very good scalability and very good performance. Downside, of course, is this is a lot more complex, right? And it's like, I just want my monolith and my single relational database, and my life would be a lot easier. The trouble is that once your systems get to a certain level of complexity, you start having to go down this route of decomposition, and then using patterns like CQRS, like event sourcing, and so on. So, so that's pretty much my talk, right? So, to summarize, right, the goal of the architecture is to satisfy these non-functional requirements. And today, given that we need to build better software faster, the key non-functional requirements are like maintainability, testability, deployability, and so on. So if you're building a small system, the monolithic architecture is just fine. But if you're building a complex application, it's very likely that sooner or later you're going to have to refactor your monolith into a set of services. But you can use the microservices pattern language to guide your decision making. And you'll very likely end up with an event-driven architecture in order to solve the problems around transactions and queries. So that's pretty much all I had to say. So thank you for listening, and I hope that you found this useful. And here's my contact info.
We can take a couple of questions. Anyone?
And I'll be around all day if you want to chat.
So what is your point of view on when you're building application or systems, right? The services is one layer that you're building as a development team. UIs is another layer that you're building. So in your experience, not only your services you have to decompose and apply microservice style or modular application design there, but what about your UIs? Because they are also expanding, and as a system, as a customer, your system will become unmaintainable if your services are pretty nice and decoupled, but your UIs are all intertwined, and you need to turn around things fast. So
yeah, that's a really good question. Yeah, in the talk, I focus on basically the back end, right? And I kind of envisage that as just a bunch of services with APIs. But let's say the front end is a web application, right? That's spitting out HTML. It's very likely that will, as you say, will be large and complex, and you can apply the same functional decomposition approach to that as well. So once again, on the online store, you could have a web application that is purely dedicated for search and showing listings of products. Then you could have another web application that is dedicated to displaying the product detail page. Right? If you actually go look at, say, Amazon.com and their product detail page, there's a humongous amount of functionality on that, right? Pricing, order history, a bunch of different kinds of recommendations, reviews, and so on. And so you could imagine that there's a significant amount of functionality that's grabbing either data from back-end services, your order history, but also grabbing HTML fragments from back-end services. So the actual product image, part of the product details page, hugely complex because you can, not hugely complex, but it's not just a simple static image, and you can actually explore it, right? And from what I understand, there is a team that just does that part of the page. And so you've got sort of this page fragment assembly model as well.
Chris, so these days a lot of people are talking about the challenge of finding the proper functional scope for a microservice, and many people have suggested to use domain-driven design and sort of try to equate a bounded context, DDD bounded context, to the scope of a microservice. Just wanted to know what's your take on that.
Oh, yeah, that's a really interesting question. I actually think there's huge synergy between DDD and the microservice architecture. So undoubtedly, so this whole thing about bounded context, right? So that's the scope of a domain model. And so certainly you can view a microservice as being a bounded context that has its own domain model. So that definitely agree with that 100%. I think the challenge that you run into is still this problem of identification, right? How do you identify your bounded contexts, or maybe more correctly, your subdomains that then map to bounded contexts? And so the concept is great, right? Like, you know, the DDD concept is you've got this big domain. Domain is divided up into several subdomains, and then for each subdomain, you define a domain model and a bounded context. That's great, but that's all it says. And it doesn't really say much about how to identify your bounded context or your subdomains. You know, it's not actually a criticism, because like business architecture, which is where this business capability concept comes from, is almost as equally hand-wavy. Apologies to any business architects in the room, but it's sort of, and actually because I suppose the other thing I would say is I sort of view business capability and subdomain as sort of kind of a one-to-one thing, kind of, sort of, but I find this whole thing frustratingly hand-wavy, right? In the sense that there's no mechanical procedure that you can follow that will give you this perfect decomposition, regardless of whether you're approaching it from business capability or DDD perspective. You just sort of, you analyze the organization, you look at the areas of expertise, and suddenly it's sort of like this creative thing, right? And suddenly the right decomposition pops out, or you iterate a few times, and then you come up with the right decomposition. So, but I am a huge fan of DDD.
Thanks.
Thank you very much, Chris.
Oh, very welcome. As I said, humbled to give a talk here.